Welcome to Section 11 of the BJCP training program from the Brewers Anonymous Homebrew Club. In this lesson, we're going to be covering the last ingredient in brewing beer, and that is yeast. And along with that, we're also covering fermentation. This is Lesson 1, the introduction to the subject of yeast and fermentation. So let's get started. When we talk about yeast and brewing in this lesson, we are dipping our toes into two pools of huge amounts of information and knowledge, and those are microbiology and chemistry. What we're going to cover about this subject in this section is the literal tip of the iceberg, and that's by design. It's what we need to know for our exams. With that being the case, we are inevitably going into some areas that are more summary explanations of what's happening with yeast and fermentation, and some of those more finer details of that are pretty much glossed over, I will admit. But again, that's what we need to know for our exams. However, if you are interested in learning much more about the specifics of yeast and their role in producing beer, this is the Yeast book by Chris White and Jamil Zainasheff from the Brewing Elements series. Just to give you an idea of the difference between the information we need to know for our exams versus the amount of information that we currently know about yeast and brewing, this section is probably going to end up being around 30 to 45 minutes when all is said and done. This book alone, this one resource on the subject, is 325 pages. But let's put all that aside for now and get into the things that we need to know about yeast and fermentation for our exams. To start off with, yeast are unicellular microorganisms. These microorganisms are of the Saccharomyces genus. Now, most beers are made with two types of yeast strains: Saccharomyces cerevisiae, commonly referred to as ale yeast, and Saccharomyces pastorianus, commonly referred to as lager yeast. These differing yeast strains function differently in their role in producing beer. The main factors that differentiate the function of these yeast strains are: they have different optimum fermentation temperatures. We'll get a little more into this later, but generally speaking, and traditionally speaking, it's worth adding, lager strains produce their optimum results at lower temperatures than ale yeast strains. They each have different abilities in fermenting various different sugars we produce in our wort. They have different abilities in settling out after fermentation is complete, meaning to drop out of suspension and settle on the bottom of the vessel and clear the beer. This is called flocculation, and the variance between their abilities to settle aren't limited to either being an ale strain or a yeast strain specifically. It varies within the substrains of both of those categories as well. Each yeast has its own unique amount of flocculation ability. You'll often see the flocculation level of each individual strain listed as low, medium, or high, so brewers have an idea of how they'll work or the time that they'll need to get their final beer to the clarity level they're aiming for. The amount of potential conversion of sugars to alcohol, which is the definition of the term attenuation. Again, this is not limited to being either a lager or ale strain alone. For example, one ale strain could be recorded to convert 71 to 74% of a wort's sugars on average, while another ale strain could be recorded to convert 74 to 78% of the wort sugars to alcohol on average. This is typically listed as the apparent attenuation for each yeast strain. And the alcohol by volume tolerance. This is the maximum amount of alcohol by percentage a yeast can thrive and survive in. Higher than this level, the yeast perform much less efficiently and even die off. And once again, this is not dictated by the yeast strain being either an ale or a lager strain specifically. Each strain of yeast has its own tolerance level. This is usually noted as the apparent ABV tolerance of the yeast strain. Different yeast strains also contribute different flavors and character contributions as well. Some British origin strains are noted for their addition of fruity esters to the beer, but Belgian strains add more phenolic notes. German lager strains are noted for their clean, light, and faint flavor contributions and producing a crisp character. When brewing any beer, the yeast strain choice varies on different factors. The first and simplest factor is what style of beer is being brewed. If you plan to brew a Belgian ale, you won't want the characteristics that, say, a Czech lager strain brings to the beer. You'll definitely want to use an ale strain. The contribution that the yeast makes in flavor, aroma, and overall character to the beer is a pretty sizable consideration as well. Building on our last example, if you want to brew that Belgian ale, you'll not only want to use an ale strain, but you'll want to use a strain that contributes that signature Belgian yeast character of ripe, fruity esters and spicy phenolic notes. The positive phenolic specifically, like that signature clove note. Taking our example a step further, let's say we want to brew a Belgian dark strong ale, and we want the alcohol range to be somewhere between 10 and 11% ABV. We won't want to use a strain that is known to have an average apparent ABV tolerance of 8%. We'll want to use a strain that we know is capable of hitting that target ABV. Now, quick note here. Yeast are living organisms, and like all living organisms, they can be unpredictable at times. A yeast strain that's known to have an 8% apparent ABV very possibly could ferment a beer to that 10 to 11% range. However, when planning out our beer, especially in this scenario, if we want the best assurance that we can get that will produce that high ABV, we'll want to use a yeast strain that is proven to hit that range and possibly beyond. A brewer might be forced, in a sense, into using a specific strain of yeast due to the equipment and the environment limitations. With lager yeast traditionally fermented at lower temperatures in the 50-degree Fahrenheit range, brewers in warmer climates that don't have temperature-controlled fermenters may be limited to using ale yeast. The good news to that is that there is a whole lot of options for yeast strains, so saying limited is a little bit of a misnomer. So this slide is not taken from our study guide. This is a little bit out of the realm of the details that we actually need to know, but to help wrap up everything that we talked about in this lesson, I put together this comparison chart to show off how different yeast strains can be used. These are 6 popular yeast strains, but by no means whatsoever all the yeast strains available to brewers. We're going to run through this quick, but do not worry about memorizing these details, especially the numbers. The details on the screen will not be in your exam. It's just to wrap up and visually explain everything we just talked about. So starting off with American ale yeast, that is an ale strain. Its apparent attenuation range is 73 to 77%. Its apparent alcohol tolerance is 11%. Its optimal temperature range is 60 to 72 degrees Fahrenheit. It's a low to medium flocculating yeast, and its character contribution is a very clean, crisp flavor characteristics with low fruitiness and mild ester production. English ale yeast, another ale strain, 69 to 72 apparent attenuation rate, 9% apparent alcohol tolerance. Its optimal temperature range for fermentation is 64 to 72 degrees Fahrenheit. Its flocculation level is high. And its character contribution, it produces light, fruit, and ethanol aromas along with soft, nutty flavors. Belgian Abbey Ale, another ale strain, that's apparent attenuation range is 74 to 78%. Its apparent alcohol tolerance is 12%. The optimal temperature range is 68 to 78 degrees Fahrenheit. It's a low to medium flocculating yeast. And the character contribution, this strain produces a nice ester profile as well as lightly spiced alcohol notes. Now, one more ale strain here. We're going to look at German wheat. Its apparent attenuation range is 73 to 77%. Its apparent alcohol tolerance is 10%. The optimal temp range for fermentation is 64 to 75 degrees Fahrenheit. It's a low flocculating yeast, and this yeast strain produces a beautiful and delicate balance of banana esters and clove phenolics. Now, taking a look at a couple popular lager strains, starting with a German lager. Its apparent attenuation is 73 to 77%. Its apparent alcohol tolerance is 9%. The optimum temperature fermentation range is 45 to 68 degrees Fahrenheit. It's a low to medium flocculating yeast, and the strain produces a distinct malty profile with some ester characters and a crisp finish. And finally, again, just as an example, you do not need to memorize these details for the exam. The Czech lager strain, its apparent attenuation is 70 to 74%. Its apparent alcohol tolerance is 9%. Its optimal temperature range is 50 to 58 degrees Fahrenheit. It's a medium flocculating yeast, and this classic strain will finish dry and malty. All right, now that we have the foundation on yeast, let's move on to our next lesson and discuss ale and lager yeast a little bit more and bring in a third fermentation organism that we haven't discussed yet, and that's because it's not a yeast. So more on that in the next lesson. I will see you there.